All right, everyone. So let's begin. And again, this is supposed to be interactive. Ask me questions, and I will ask you questions too. So I'll give you this, start with this very simple problem. I'm going to build up from here. We have to compare two strings. I have two strings. I've shown all the symbols of the string as a string of beads, just for visualization. And I want to compute the distance between these two strings. Now, how would you do this? You guys have done this several times. So Kathleen, maybe you can tell me how you'd go about doing that.
I'd compare how much overlap there is.
How do you compute? How do you quantify overlap?
Well, I guess begin by seeing if the strings have the same length, and then splitting them at equidistant points, and then measuring the different segments.
And maybe you have a different answer? Your mic is off. Yeah.
Oh, yeah. So I was thinking of something like what it says on the slide. So sort of like an edit distance sort of thing. So you try to find as best as you can some sort of alignment, and then you see what it would take from one string to be converted to the other string.
Exactly.
The cost
right?
of.
So you want to align the two strings and then try to find how much difference there is after the two are aligned. Kathleen, your answer was kind of halfway there, but here's what we would do, right? I have these two strings, they are different lengths. So firstly, if I'm going to assume that one of the strings has been obtained by distorting the other string somehow. So I've got to sort of figure out what the various ways of distortion are. So here are two examples of how I could align the second string with respect to the first string. Let me see if you can see my mouse. Where's the pointer here? So I could align it like I have in this first case, where I take the second string, I stretch it past the first symbol. So I've aligned up the two B's, I've aligned up the A, but then I have these two extra B's in between, which are kind of hanging. Then I stretched it past these two A's, I aligned up the C and the B, but then these two C's are hanging. And then this A, I stretch it past the A, I managed to align up the D's, C's, and A's, and these two D's are hanging. Now, when you look at this guy, you observe that I have managed to match 1, 2, 3, 4, 5, 6, 7, 8 symbols. But in the process, I have stretched it past this guy. So here's one error, here's one error, here's one error, here's one error. These are what you call deletion errors. You have deleted symbols from the first string in order to make them match. Then in the process, I also made things hang. So these guys here, they're hanging. They are what you call insertion errors. They are spurious symbols that you've had to insert in the second, that you've inserted in the second one, which makes them mismatch. So if you compute the total number of errors over here, it's going to be 1, 2, 3, 4 deletion errors and 6 insertion errors. That's going to be the cost of aligning this string to the second one in this manner. But that's not the only way of aligning the two. Here's a second way of aligning the two, in which case I'm still stretching it past the first B. I'm aligning B, B, and A as before. But instead of stretching it past these two symbols here, as I did over here, I'm going to let it continue, in which case I get C, 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 and B. I stretch it past this A, and then I align them like so. When this happens, you see different kinds of errors. Earlier, we had these deletion errors, and we had these substitution errors. Now, I have a deletion of an A, I have a deletion of another A. These two B's and these two D's are inserted. But then over here, when I align them up, the symbols are wrong. So there's a difference. So I have two what are called substitution errors. And so the cost of aligning the second string to the first guy in this manner is 2 deletion errors, 4 substitution errors, 2 insertion errors, and 2 substitution errors. You see what's happening over here in these two cases, Kathleen?
Yes, I do.
Ayodele, do you see what is happening here?
Yes, I did.
Okay, so now each of these two is going to end up with a different cost, right? Because depending on how I stretch and shrink or the second string, I'm going to get different kinds of alignment, and each of them will have a different cost. I'm going to choose the distortion that I'm going to figure that the number of changes I had to make to the first string to make it the second guy were really small. So I'm going to search amongst all possible ways of distorting the second string so that it aligns up with the first string. And then for each of these possible ways, I'll find the cost of the alignment, and then finally pick the one for which this cost is the lowest. And that is going to be the cost of matching the second string with the first string. So I'm going to the cost of matching a data string to a model string. In this case, I will call the second string, which I'm stretching back and forth, as my data string, the first string, which is my template, which I'd never modify, as my model string. And the cost of matching a data string to a model string is the cost of the alignment that results in the lowest cost. Now, if I want to actually compute this, how much computation would it take if I did this naively? Leon? Can you tell me? You're muted.
Could be n squared.
Actually, it's going to be exponential, because remember this, I could do all kinds of bizarre things, right? If I could stretch this thing straight past, make everything hang, and get a completely wrong alignment, I mean, completely bizarre alignment, and I could do it in any number of ways. I could make things hang further and further down. So the number of possible ways of aligning the one to the other is exponential in the length of the string. This means that if I want to find this alignment which results in the lowest distance, if I did this kind of naively, I'd have to search the exponential number of possibilities, which doesn't make sense. So we're going to use a dynamic programming algorithm. Now, those of you who worked with this in the past, you know that you use the Levenshtein distance computation algorithm. I'm going to use a slightly different algorithm, which still will give you a very similar result. I'm going to call it dynamic time warping. The way we do it, you're going to incrementally build up best alignment by matching substrings to entire strings. This is a standard procedure, and it's what we call computing the Levenshtein distance. The standard way of doing it is not possible to represent in a manner that I will be using in this lecture. So the actual procedure that I'm explaining is a variant on it, where I can build a static graph. You may not have any idea what I'm talking about at this point. You will in a few minutes. So here's what I will do. Here is my model string on the vertical axis. Can you see it? Here is my data string on the horizontal axis. So what I will first do is to align the shortest of my substrings, which is just the symbol B, against every substring starting from here of this model string. So if I align B with A, what would the cost be? If I align just this B with this A, what would the cost be here? Anyone? Tanmay?
One substitution cost.
It's going to be one error because a B is not an A, correct? Suppose I align this B with AB. What is this cost going to be? Are you there? Are you there? Are you there?
Yeah, I'm here. I'm trying to.
What would the cost be?
Not sure I have an idea.
Yeah, look at this. If I align this B to AB, what would I have to do? I can do two things. I'd have to stretch this B till it came up here, correct?
Okay. Okay.
In the process, I'm skipping the A.
Okay.
Right? So B matches a B. There is no error, but I skipped an A. So I got a cost of 1.
Okay.
Make sense? Right?
Yes, I think so. Yeah. So you skip one, then you move to the next one.
So Kathleen, what would the cost be for aligning B to ABB?
2.
2, because the B is going to match up with the B and there are errors. What about aligning this B to ABBA? What would the cost be?
I have a question. Why are we
Yeah.
not inserting after aligning?
Pardon me?
How come we're not inserting after aligning? Because if we want the B to align with AB, for example, we stretch the B and make it align to the B, and then we insert an A, right?
You don't insert an A. This is all you've got. This is the string you've got. Right. I'm trying to align just this B. So you are not going to ever insert anything. When I spoke of an insertion error over here, it meant that when I distorted the second string, some of the beads hung at the bottom, correct? It's like saying that when I modified this guy to make this one, I inserted some spurious beads. That's why they're hanging. So, but the beads were very much part of the string, right?
Okay.
So if I align just this B to A, B, B, A, what would the cost be?
Would it be 3 deletion costs and 1 substitution?
That's correct. And if all of them are equal, it's going to be 4, correct? And so you can align this little string to every substring all the way to the top. This is easy. Now, I'm going to use these numbers to figure out how much it costs to align BB to every one of these substrings. Okay? So now let me try aligning BB to just A. There's only one way of doing that. I'm going to align the B to an A, and I'm going to let this B hang, right? So that's going to be a cost of 2. If I'm aligning this BB to AB, then this B must align to A, and this B must align to B. Remember, we are looking at the lowest cost alignments at each time. So this is going to have, because the B matches the B, there is no cost. This B is not an A. So it's going to be the cost of this guy plus the cost of aligning the extra. So you see what is happening over here? I first align B to every one of these guys. Now I'm going to say, what is the cost of aligning this extra B to the extra symbol here? Okay. So I can align B to A and then the subsequent B to the next B. Or if I want to, let's say if I'm aligning BB to ABB, there are 3 ways of doing it. I can align B to A, and then I can align the second B to the next BB. Or I can align B to AB, and then align the next B to just this extra B, right? Or I can align B to ABB and have this guy just hang. So there are 3 ways of aligning BB to ABB. Do you see how there are 3 ways of doing it here? Right? Kathleen?
Yes, I see that.
And so if I want to find the cost of aligning BB to ABB, I'm going to pick the lowest of the 3, which is to say, I'm going to say, I have 3 ways of doing it. It's the cost here, plus the cost of aligning this B to this extra BB, which is this edge. The cost here, plus the cost of this edge, which is the cost of aligning this B to the final B. Or the cost here, plus the cost of letting this B hang, which is this horizontal edge. There are 3 different costs. I'm going to pick the lowest one, and I'm going to assign that as the cost of aligning BB to ABB. And so now I can do the same thing and work my way up and align BB to every one of these guys. And then I can go to the next step, right? And repeat. Now that I've got the scores at these points, I can figure out the cost of aligning this extra B to whatever is left over. So the cost of aligning to this BBB to any substring over here is going to can be computed as the cost of aligning BB to these places, plus the cost of the extension. And at each point, you're going to pick the lowest cost. It's just the same algorithm repeated over and over again. Make sense?
I have a question.
Yeah.
For the y-axis, the substrings you're taking seem to always
start from the beginning. Yes. Yeah, you lost your mic.
Sorry. Can it be any substring, or does it have to start with?
Starting from the beginning.
But then what about if the first B was matching with, let's say, the 6th B in that substring?
So there's one kind of error that you see that that I'm not actually considering over here, right? You don't have these connections coming down. That's all. But you could do that. If you want to do that, you would have to say, what is the cost of aligning this B with a negative string? There's no notion of a negative string.
Okay.
Right. So that is the equivalent of saying that when I make things hang over here, I'm not allowing this thing to hang for an arbitrary length.
Okay.
Correct?
Yeah.
So that's all. I mean, so this is not your standard Levenstein algorithm, but this will work. So I can work this, compute this distance, compute it for here, and work my way all the way to the end. At each time, I'm performing n computations, right? When I come over here, I will eventually get the cost of aligning this final bead to this final bead. And that's going to be the cost of aligning this entire string to this entire string. In the process, I've also found out exactly how each of the symbols was matched to each of the symbols in the data string was matched to each of the symbols in the model string. That has also been computed. So I actually end up getting this little alignment graph as well. Right? Now this is key. I'm going to build everything off of this. So do you get it? Adlai, do you get it? If you have any questions, ask.
Yes, I have a question. So if we leave the next letter hanging, that means that anytime we want to align another word, it might not be taken into consideration.
So here is what it is. Like I'm not allowing a certain kind of thing. I'm not allowing negative strings over here. That's all I am doing over here. Okay. But I can keep adding things over here along the x-axis, and the whole same process will keep continuing.
Okay. Okay.
Correct? I'm trying to find out which of these symbols some guy aligns to. That's all. Everything must align to something, right?
Okay.
Leon, that makes sense?
Yeah.
Okay. So this is key, right? And now here is what happens. I can view the whole thing as a graph search. What I could have done was to compute this graph. I could just have drawn this graph. Observe all of the comparisons being made over here, right? At each point, when I want to compute the cost of aligning this fellow to this substring, I am comparing 3, 4, 5, 6, any number of incoming edges, as you can see, correct? So basically what I've really done is constructed a graph of this kind where every node represents an alignment of one substring over here to a different substring over here. And each of the edges shows you the alignment of local substring. So for example, if I look at this edge shows me the alignment of this extra B with just this A. If I look at this edge, it shows me the alignment of this local B with just this extra B. Or if I say consider an edge which goes from here to here, that is showing me the cost of aligning this extra B with BBA. And so to answer your question, Tanmay, everything explicitly ends up getting considered. Make sense? Right? And every single cost is built into this graph. So Adlai, Kathleen, that makes sense to you?
Yes, it does.
Okay. So I'm just going to assume that you understand this. It's not so hard. If you don't, you can go back and look at the slides. From here, things take off, right? And what we are really doing is finding a best path through this graph, because every edge has a cost. We are simply finding the best path through this graph. And so this is the entire process of aligning two strings. But then that's not what we really want to do. We are performing speech recognition. But before going into that, keep in mind that this is just one way of constructing the graph. The graph is asymmetric in the sense that every symbol along the horizontal axis must be visited, but we are permitting the alignment to skip symbols on the vertical axis. So the distance is not symmetric. The distance between string 1 and string 2 is not the same as the distance between string 2 and string 1. Also, I can construct the graph in other ways. I can make it symmetric. I can say the symbols on the horizontal axis may also be skipped. or I can incorporate additional constraints where we can say you don't permit the edges to skip more than 2 symbols along the vertical axis. You can do all sorts of things. That's kind of slightly beside the point. The point is that what we are eventually doing is constructing a graph, assigning a cost to every edge in the graph. And the cost of every edge is the cost of aligning some substring to some other substring. And then we are finding the best path through this graph, right? So now, instead of trying to compare 2 symbol sequences, character sequences, I can also try to compare 2 sequences of vectors. So if I have a sequence of feature vectors and I have another sequence of feature vectors, I could use essentially the same algorithm to say what is the distance between these 2 sequences of feature vectors, which could potentially be of different lengths. And the procedure is going to remain pretty much identical with one small difference. The small difference is that over here, when this symbol here and this symbol here were identical, we assigned a cost of 0. When they were not identical, we put a cost of 1 at the node, right? Instead, if these are vectors and these are vectors, the cost that we will put at each node is going to be the distance between the 2 vectors. And the distance can be computed using any kind of metric, like a Euclidean metric or a Manhattan metric or a weighted Minkowski metric. I don't really care. The point is it's still going to be computing a distance. And once I assign a distance on every node, then I can find the best path through the graph. And the cost of the best path through the graph is going to be the cost of aligning the 2 vector sequences. That makes sense to everyone? Right? Leon, Adlai, Kathleen? I need your yes before I proceed.
Yes, yes.
Yes.
Yep.
It doesn't sound very convinced. You'll have to go back and look over the slides. The first 15 slides are the entire story. You know how to do that. You know how to do speech recognition. It's that simple. Okay. So now let's say I want to perform speech recognition. And so I'm going to take you back 20 years. Not today's speech recognition systems, but say back to 30 years, 1990, okay? And you want to build a little speech recognizer which recognizes digits. What would you do? You're going to store 1 or more examples of yourself recording each of the digits. Or say you're building a phone dialer. You're going to store 1 or more examples of yourself saying each of the names you would like to dial. And then when you want to dial somebody, you're going to say a person's name. And the system is going to use the algorithm that we just used to compute the distance between your new recording and the recordings that you have stored. And it's going to pick the recording for which the distance is smallest. Very simple distance-based matching. Make sense? Right? There's nothing particularly novel. The most difficult bit was the algorithm itself, which wasn't very hard to begin with. Now, when I speak of a speech recording, I'm not really going to be using the samples by themselves. I'm actually going to convert the speech recording into a sequence of feature vectors, typically Kestrel vectors. There's an entire process for converting speech recording to sequences of feature vectors. I have one process on the slide over here. I won't actually go through it. But regardless, what you will typically get is 1 feature vector for every 10 milliseconds of speech. So you're going to get of the order of between 100, or if you're particularly conservative, 30 feature vectors per second of speech. So if you record a 5-second utterance, you're going to get between 150 and 500 vectors. And that's what you will store. When you store your digits and you want to build a dialer, you're going to store these extended sequences. And then when you record a new instance, that is also going to be converted to a sequence of feature vectors. And that is what you will be comparing against your recorded instances to pick the closest one. So that's it. You're going to have very little more math from here for the next half hour. So here's what happens. I want to build a phone dialer. I'm going to record myself saying the word digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to store 1 instance of each. And then when I want to call somebody, I'm going to go and say 0. the system will compute the sequence of feature vectors from my new recording, align it to each of the recordings that I have stored. The alignment is going to give you some best path, but it's also going to give you a best path score. And it's going to pick the recording for which the score was smallest. And so you found out what number you just said, right? What are the things that can go wrong with this simple procedure? Anyone? Then maybe you can tell me.
So just a small doubt before I answer that. What is each vector in this?
Each vector, basically, I said, any recording is first converted to a sequence of feature vectors, right?
Okay.
So each recording is eventually going to become something between a 15 and 50 dimensional feature vector, a sequence of, feature vectors where the feature vector length could be anything from 15 to 50.
So I guess one problem would be that it will only match the recordings that you have. You won't be able to.
It's only going to match the recordings that you have. That is going to be a key problem, right? A person can say the word zero in many different ways. And so, in fact, you are never going to say the same word twice in exactly the same way. So if I want to just recognize the digit zero and I have 15 different ways of saying the word zero, would it be enough for me to store just one instance of zero? Not really, right? I'm going to have to store all the different ways in which I can say the word zero. So I can store multiple templates for each word. For example, record 5 instances of 0, 5 of 1, 5 of 2. And then when I'm what I will do during recognition is, if I have this in the next slide, say I have 4 instances of 0. If I want to find the cost of 0, I'm going to align my input against every one of these 4 instances of 0. Pick the one for which the cost was lowest. And I've not only found the cost of aligning to 0, but the best, how I actually set the 0. I would do this for each of my 10 digits and pick the digit for which this cost was the lowest. Make sense, everyone? Ayodele? Guys, you know what? Can you turn on your camera?
I have a question. Sorry,
Yeah.
I have a question. So you are going to take each of the ways by which the words is spoken, then align it to check the best. But what if maybe you have 2 words that have similar what they call evaluation, that they seem to be the best, and you can't really pick one?
At that time, it's random. So by the way, so the 2 of you who have your cameras turned off, I want you to turn your cameras on. I like to know you're watching.
Just a minute.
Yes. Thank you. I really you too. I really appreciate that. This is my only way of ensuring that you are paying attention, right? Okay. So, but you got what I'm saying over here. Make sense?
Yes.
Okay. Right. So what is the problem here? There aren't just 4 ways of saying 0. There are maybe 4,000 ways in which you can say 0. And unless you actually recorded every one of these, you can't be sure that you're doing a good job. And the cost is going to blow up really quickly for making these alignments, right? So finding the closest template requires evaluation of all the test templates. And even if you do that, the set of templates that you record may not cover all possible variants of the words. So you want to be able to generalize from the few templates that you have recorded to other ways of saying the words that you may not have recorded. And one way to do so is by averaging the templates. So here's what we can do. Now I have stored all of these 4. I have recorded, let's say, these 4 instances of 0. And I want to find an average 0, a typical 0, correct? So I can start out by saying I'm going to use this T4 as my base template. Then I'll align T3 against T4. And when I align it, it basically also tells me how to stretch and shrink the symbols. stretch and loosen the string so that it aligns up. I can do this for every one of the other three. And when I've done it, I have aligned T1, T2, and T3 against T4. Then I can just go down each column, find the average, and I'm going to get some kind of an average model. Now, this is a really crappy idea. And Leon, can you tell me why?
I'm not sure.
So, anyone of the rest of you? How long? Yeah.
It sort of takes away the benefit that was coming from 5 different pronunciations.
Well, averaging is required. You want to generalize. Here is the bigger problem. How long is the final template going to be? Leon? It's going to be as long as the first template that I picked up, correct? If I picked up T4 and then aligned everything else to T4, the final template is going to be as long as T4. If I picked up T1 instead, T3 instead as my base template and aligned everything else to that, the final template is going to be as long as T3. So this is a non-standard process. Depending on which order you look at your inputs in, you're going to get something completely different. So this doesn't make a whole lot of sense. So
I have a question.
Yeah.
If this T1, T2, T3 were feature vectors, then
feature vector
they be
sequences.
of
The feature vector sequences.
Yeah. So
every time you say 0, 0 is going to be a different length.
Okay.
Correct?
Yeah.
So it's never going to be the same. So you have a problem, right? Now, here's a different way of constructing an average, which is kind of more, somewhat more standard. I could do this even with a single template. I can just take my template which is a sequence of feature vectors. I can chop it down into 3 segments with these, virtually chop it like so. And then I can compute an average of all of the vectors over here. I can compute an average of all of the vectors over here as well. And I can compute an average of all of the vectors over here as well. And now I have this average template, which has only 3 vectors in it, which somewhat captures the average, which captures the characteristics of this guy, but I've done some averaging. Now, you're probably going to say that in this process, I'm losing the information about how things change continuously. You would be right. But still, I've come up with an average. It's a trade-off. I want some template which will generalize. And in the process of averaging things, I might have made it generalized. Okay? But it's not, but then, and then if I want to perform recognition, I can just use these average templates to compare against my input and find which template matched best, right? So how would I extend the same idea if I recorded myself saying the word 0 4 times? Now I have 4 example recordings of 0, correct? I want to build an average template. So here's what I can do. I can chop each of these guys uniformly into 3 segments. And then I can compute my average where this first bead comes as the average of all of the first segments of all of my examples. The second bead comes as the average of the second segment of all of my examples. And the third bead comes as the average of all of the third segments of all of my examples. And so now I have an average, a properly averaged template, which has been averaged over multiple sequences. And now I can use this guy to perform recognition. You with me still? Right? Nothing, we haven't done anything fancy, nothing that you couldn't write a little bit of code for. So, and now.
Sorry, can I ask a question? Sorry, can I ask a question?
Yeah, sure.
Sorry, what's the basis to pick 3 what they call dimensions?
Just 3 segments, you mean, right? There isn't any. So that's a very nice question. I wish I had an answer. The fact of the matter is nobody knows how many segments is a good number. We just go with it arbitrary. We just go with an arbitrary choice. In my example, I'm using 3. In real life, you're going to be a little smarter than that, right? For example, if I were to look for the word zero, the word zero has 4 phonemes in it: Z, Z, E, R, and O. So you need to have at least 4 segments. But then phonemes themselves change. Typically, you need 3 segments to even model a phoneme. So that means you're going to probably need something like 12 segments. There's a certain degree of heuristic over here. I'm just using 3 as my example. Don't fall for it, okay? So there was something else over here that was wrong. There were several things wrong, incomplete even about this procedure. Can you suggest what might have been wrong? What you could do, like, how you could adjust this process? Kathleen?
You could think through better segmentation.
Thank you.
So that you have, yeah.
Okay. That's exactly what I was looking for, right? Look at this. First, let's look at how things happen, right? Now, if you look at these beads represent values, the colors in these beads represent values. If you look at the inherent variation between vectors in these different segments, there's a lot more consistency over here than there is over here, right? So, and again, what we do when we are performing the search over the graph is that you're comparing vectors to vectors, you're computing distances, and you're finding the best path based on the distance. But now suppose this is my feature X, I'm trying to, right? And suppose for this cluster, if I plotted the histogram of values, I got a histogram like this. They're all very close. And for this cluster, let's say I got a histogram which was like this, because they are much more scattered, right? And then on my test recording, I got a vector which was here. Are you going to say it's closer to A, or are you going to say it's closer to B? Which of the two would you pick? Tanmay?
A, I guess, because you could be more sure, but I don't know.
So Leon?
I would guess A, but I'm not quite sure why.
Okay, I'll tell you why it's not A, right?
I think it's B.
It has to be B because the vectors in A don't like to spread out.
It's spread.
The vectors in B don't mind spreading out, right? So this guy is more likely to have come from B than A. So you really want to account for the natural spread of the data before you begin computing distances, right? Now think of it this way. Suppose I have 2 alignments, one in which I get a smaller distance because I align it to A, and a larger distance because I align it to B. Should I be accepting that alignment? I really shouldn't, because there's no way A would actually go this far out and generate this guy, whereas B could have. I have to account for this inherent spread in the data. And so what I will do is I'm going to compute the covariance for each segment using the standard formula for covariance, which tells me the spread of the data within each segment. And then when I compute the distance, I'm actually going to normalize out the covariance. So skip the math. What this really says is that this naturally accounts for the spread in the data in each cluster. And you normalize for it so that when you compute the distance between 2 vectors, if the data has a natural spread that is large, you're going to compute a lower distance. than if the natural spread is small. That makes sense? By the way, that makes sense?
Yeah, exactly. Yeah.
Yeah. Kathleen? Yeah, okay. So that's one problem. But here's the second problem that Kathleen mentioned. Simple uniform segmentation of training instances is not going to be the best or the most effective method of grouping vectors. For example, I might have said 0 the first time around, and the second time around I might have said 0. And the difference was that in the first case, my Z was long, and the second case, my Z was short. If I segment both of them uniformly, I'm going to take a whole bunch of O's from my second instance of 0 and begin grouping them with the Z's in my first instance of 0. That doesn't sound right, does it? So what you want to do is to make sure that you're consistent, that when I segment two instances of 0, the first segment will always get the Z, the second segment always gets the O, and the third segment always gets the rho, right? That's what you would like to do, to make it representative of the word 0. The problem is, nobody's telling you, sitting there and marking off the boundaries. You have to figure this out yourself. There's a different way of thinking about it. I'm going to think of it as consistency. So I want every segment to be locally consistent in terms of distance. And I want to compute my segmentation such that I maximize the consistency within the local segments. So I'm going to do that iteratively. I will start off by initially segmenting everything uniformly, so I get my average model. And then I'm going to pick up this first guy over here and try to align it against my average model. And what will happen is when I align it, I'm going to get an alignment of this kind. And it's going to tell me which of all of these guys align best with this first vector. Which of all of these guys align best with the second vector? Which of all of these guys align best with the third vector? And what happens in the process is that I have a new alignment, right? This was the old alignment where I aligned everything, where I segmented it uniformly. But then when I went back and realigned it against the average model that I just picked, I got a new alignment. And this new alignment is more standard, more representative of this model than this guy. Does that make sense? Right. So, yeah. When I ask you if it makes sense, I expect you to raise your hand or click on some button, because I'm just going to keep going on. Yes. Okay. But that's just the first guy. I can do the same thing for the second guy and the third guy and the fourth guy, and now I have resegmented each of these 4 into 3 segments. And now this group of yellows is a lot more consistent than what I began with. The group of pinks is more consistent than what I began with. The group of blues is more consistent than what I began with. I get a new model. But why stop here? I can repeat the process. And I can keep doing this till the segmentation stops changing. And that is going to give me my new model. And that's going to give me a more consistent model for each of my words. And so that is going to give me a more consistent and an updated model. But then something strange happened over here in the process. We've sort of gone from having these templates represent actual recordings to represent something virtual, meaning this model that you might have computed might represent a sequence of feature vectors that have never been seen, and that could virtually never even be seen. They're averages, correct? And for that reason, I'm going to call this a model at this point. They're segment boundaries. The model has 3 states. Each state has a mean, which is the typical vector for that state. Each state has a variance, which tells me the spread of vectors for that state. This is just a change of terminology, but nothing really has changed, okay? And so we're going to use these converged models to align our incoming data sequences And so if I'm trying to build a digits recognizer, I would have one of these. I would have gone through this training procedure for each of my 10 digits, built an average model for each of my 10 digits. And then when I get my test recording, I'm going to compare it against my average model for each of the 10 digits and pick the one for which the distance was smallest. But I'm still not done. There's one more issue. And the issue is this. Look at this. After I'm done aligning things, resegmenting things like this, the segment lengths have all changed. They are not all the same length anymore, right? They have segments which tend to say consistent longer, like vowels will end up giving you longer segments. Sounds like t will give you shorter segments. The segment lengths are not going to be the same. But then suppose I gave you a recording and I began performing an alignment, and the alignment somehow, say, gave me, when I aligned it, I got a really low score, really low cost. But in the alignment, I found that the yellow segment was short and the pink segment was long. And the second best alignment gave me a long pink segment and a short pink segment and a long yellow segment. Which of these two should I believe?
I think the one that gave a longer segment.
The one that gave the longer yellow is more believable because it's also following the physical characteristics of the data, right?
Yes.
Even though just based on the simple basic cost, the first guy ended up giving you a lower cost. This means you have to tweak your alignment process and you have to make it so that the alignment process itself naturally favors long yellows and short pinks, so that you have some natural mechanism for picking up preferring alignments where the alignment to yellow is longer than the alignment to pink. So to do that, we're going to introduce something called an insertion penalty. And what that means by an insertion, what we mean by an insertion penalty is something like this. So for every state of the model, I'm going to have an insertion penalty. I'm going to assign penalties to every kind of transition. We will see what this means. If a blue alignment to a blue bead is followed by an alignment to a blue bead, I'm going to give it a cost of T11. If an alignment to a blue bead is followed by an alignment to a green bead, I'm going to give it the edge a cost of T12. So these are edge costs in my graph. The node costs were the distances between these two nodes, right? But I'm going to insert an edge cost. And the edge cost, these horizontal edges represent this, what I call the self transition. The diagonal edges represent what I call a transition from here to here. And I'm going to assign a cost to each of these guys. And the way I will choose it, if I see that and once I begin allowing edge costs of this kind to generalize, it's like saying, I also have an edge cost of completely skipping the green, but this is infinity. So I can begin introducing other arcs in this graph. Anyway, so what will reasonable edge costs be to make the whole model work? We are going to do this with probabilities. For segments that are typically long, like our yellow segment.
Sorry, just a question.
Yes.
Yeah, so the number of penalties we are going to choose will be determined by the number of maybe the alignment that exists between the variables around. Am I right?
I'm not sure I understood the question. Can you repeat that?
So the number of penalties, like you want to pick that what is going to follow the next one, whether if it's a blue color, the next one. So remember the DTW alignment that we used. We are using that everywhere. Okay.
So that first few minutes of the lecture, you have to assume that every time I draw a figure like this, I'm composing a graph, I'm putting in the edge scores, node scores, and finding the best path. And best path is going to give me the alignment.
Okay.
Make sense?
Makes sense.
Yeah. Okay. So what would good costs be for these alignments such that, they naturally favor the right length for each of these segments. And a good cost can be based on probabilities. A good choice for transition scores are the negative logarithm of the probabilities of the appropriate transitions. So I'm just going to skip that. I said no math, well, I lied. Here's a little more. But look at this guy. In this segment, when I did my alignment, this first segment first training instances had 6 vectors within the yellow segment. The second one had 3. The fourth one had 5. The third one had 5. The fourth one had 6. So the total number of vectors within the yellow segment is going to be 6 plus 3 plus 5, that is 9 plus 5, 14, plus 6 is 20, right? Of the 20 vectors that happened within the yellow segment, 16 were followed by other vectors within the yellow segment. Only these final 4 were followed by vectors in the pink segment. Correct? So if you are in the yellow segment, the probability that the next vector will also be in the yellow segment is 0.8. If you're in the yellow segment, the probability that the next vector will be followed by a vector from the pink segment is 0.2. 4 over 20, right? So if I take the negative of the log of this probability, it's a peculiar operation. Basically what this means is that things that are impossible, the log of 0 is going to be minus infinity, correct? And so negative log of that is going to be infinity. So things that are impossible will give you, if I want to make a skip from here to here, that's like an infinite cost. If I want to stay within this guy, that's minus log 0.8, which is going to be a pretty small number. And if I look at this guy, that's going to be minus log 0.4, which is going to be a larger number. If you're always going to stay within the yellow segment, the probability that the next yellow segment of vector is also from the yellow segment is 1. Log of 1 is 0. The cost will be 0. If you're always going to go out, if there's a segment in which you never spend more than 1 vector, then the probability of exiting is going to be 1. The self-transition probability is going to be 0. So the minus log of the probability is going to be infinity. So the horizontal edges will have infinite cost. The diagonal edges will have 0 cost, right? So this negative log kind of works out. So in our example, so that's basically the arithmetic over here. I'll skip that. Now, once I do this, I can actually begin drawing these other kinds of arcs. I could draw this arc over here, which says that when I draw my graph, remember the DTW graph only allowed certain kinds of edges. I could say I'm allowing you to go from this guy and skip this one entirely. So in the graph, I'd actually have a longer diagonal edge. And I just try to figure out the penalties associated with those edges if I'm trying to learn a model for my data. You can allow all kinds of structures within your model, but not go there right now. So all of this gives me one. I'm going to incorporate all of these into my algorithm. I'm skipping a lot of the arithmetic because it might just get a little painful. But here is what we want to do. We want to also learn these T's in the process of learning the model. Okay. And so the overall process is going to look something like so. I'm going to start off by initially segmenting all of my data uniformly. And then I'm going to learn not just the means and the variances of for each state, but also these penalties. Now, clearly from this segmentation, you know that this penalty is infinity, right? But you know that this penalty, the cost of staying within a yellow is quite small. The cost of going from yellow to pink is slightly larger, right? Using these costs, I'll perform my alignment, get new segmentations. using those new segmentations, I'm going to recompute the means and the variances and recompute these costs and keep iterating the process until the whole process converges. That's what we will call our segment. This algorithm is called the segmental k-means algorithm. Again, the terminology is kind of not important. The concept is important. Okay. So I'm assuming that at this point, we've gone quite slowly through the process. But I'm assuming at this point, you have sort of got an idea of how I could build a well-defined average template for the word zero from a bunch of examples of the word zero. Leon, questions? Kathleen, Adlai?
No questions.
No questions. This might be a bit too fast for you, but the slides will be available. You can go through it slowly, okay? So this model is a general statistical model for processes that generate time series. The segments in our time series are what we call states. And it's actually one generalization of the DTW models we've discussed so far. In fact, there's a name for this model. Once you begin introducing these transition penalties, it's called a hidden Markov model. So an HMM basically consists of this. It's got a sequence of states. Associated with each state is something of the nature of a mean and a variance. Associated with each state is also a transition penalty or a transition probability, which tells you what is the probability that the next vector also comes from the same state, or that the next vector comes from the next state. It has two components to it. The first is this underlying structure, which tells you which state can follow which state. And the second component, which tells you how to compute this, will give you the structure of the graph that we used to find the best alignment. The second one consists of the means and variances of these guys, which tell you how to compute the distance between a model vector and a data vector. So these are just the two components of the entire model, and these two together give you an HMM. Now, an HMM is basically similar to a dynamic. In fact, you know what? Instead of going through the slides, which are likely to be confusing, let me go back and use this figure over here. Now, what we did here was we used all of these guys to compute the mean and the variance, correct? What was the purpose of computing the mean and the variance? That was because when I gave you some new test recording, for each vector in the test recording, you wanted to compute the distance between that vector and this state, right? And that you did using the mean and the variance. It turns out there are different ways of doing it. You can do it statistically. You can just look at all of these vectors and say these are all examples of the first state. You can look at all of these pink vectors and say these are all examples of the second state. You can look at all of these blue vectors and say these are all examples of the third state. And now, if I give you a new vector, I can learn any function which tells me what is the distance between this vector and the first state. What is the distance between this vector and the second state? What is the distance between this vector and the third state? And that function can be anything. That function can also be a neural network. So it doesn't just have to be a simple mean and variance. In the process of segmenting things up like this, I have actually made collections of data. I have all of these examples of vectors which belong to state 1, all of these examples of vectors which belong to state 2, all of these examples of vectors which belong to state 3. And this collection of data can actually be used to train a neural network, which can take in a new vector and give you a score for each of these states. Make sense? Did I lose you? I made a giant leap of faith over here. I threw away the mean and the variance that we just computed and replaced that with a neural network. All right, Relay? Did I lose you?
No.
Okay. Kathleen? Okay. I'm going to assume that you understood it. I'm skipping all of the complex stuff here. And I prefer to go with pictures because I don't think math is very good over Zoom. Okay. But then, so now suppose I want to actually train a model for the word zero. What am I going to do? I'm going to record lots of examples of the word zero. I'm going to convert each recording into a sequence of feature vectors. Then I'm going to use this little algorithm. I'm going to define some components, how many segments, how many states I'm going to have for zero, which state can follow which state. This I will predefine. This is heuristic. We don't have a proper algorithmic way of actually deciding this. And then we're going to use the algorithm that we just described to learn all the parameters of the model, which should be these transition scores and possibly the parameters of the neural network that assign us a score for each state given an input. Okay. So now something interesting happens in the whole process, right? Let's see. I'm going to try to skip the math. Okay. Actually, this is something that can't be avoided. Now, if you look at in the process of computing an alignment, what are we actually computing? What we are actually computing is the distance between the input data and the template under the best alignment, right? That's basically what we said we were doing. That distance can be thought of as a log probability. So it's basically computing this term over here. So let's say I'm considering the word zero. Then what the distance is going to be the negative of the log of the probability that the specific input that you got could be an example of the word zero. This bit you're going to have to take on faith, right? And that's why we could also model the transition scores as negative log probability. And so once I do this, the whole problem of finding which word was spoken becomes a problem of Bayesian classification. Now, this is the second key concept that we're going to bring in. In Bayes classification, you're always picking the class which is most likely given your input. So in other words, you're going to pick the class for which the probability of the class given the data is maximum. I can write it as saying the class for which the log probability of the class given the data is maximum, or the negative log probability of the class given the data is minimum, which sort of decomposes to this. You're picking the class for which the sum of the cost given by your dynamic time warping model and the negative log probability of the class itself is minimum. Now, what does all of this mean? Suppose I have a recording and I want to find out if it's the word zero or the word one. And then I find that the cost of the word zero is 0.9, the cost of the word one is 0.95. But then I know that in my world, no phone number begins with the digit zero. I've never encountered a phone number that begins with the word digit zero, right? So should I be thinking, if I know that this is the first digit, should I be choosing 0 or 1? Which would make more sense? Anyone?
1.
Because 0 doesn't happen, correct? In the first.
Yeah.
How do you factor that in? So what I'm going to say is I'm going to add this extra penalty, which is the negative of the log of the probability of the class. Why negative log probability? Because when the probability is 0, minus log probability becomes infinity, right? So you're basically saying there's no way in hell this phone number began with the digit 0. And so you're going to be summing to the cost that you got for alignment the negative of the log probability of the word itself to get the final cost, and you're going to pick the class for which this cost was minimum. Did that make sense? Try to skip the math. Leon, did that make sense?
Yes, it does.
Okay. So fine. Now let's get into some more pictures. So let's say you want to record, you want to say that you have only two words in your language, odd and even. And you want to find out if a person, and then you record a new word, and you want to find out if the person said odd or if the person said even. What is the obvious thing to do? You're going to train a model for odd. You're going to train a model for even, right? And you also want to factor in this a priori probability of odd and the a priori probability of even. So you're going to just stick that into this edge, the incoming edge, as an extra penalty, okay? And then when I get a new recording, I find the best path through this guy. I'm going to end up with a cost out here. I'm going to find the best path through this guy, and I'm going to find the cost out here. The cost here is the cost of odd. The cost here is the cost of even. I picked the word for which this cost was minimum. This is just exactly the problem that we've spoken about. Right? Make sense? I can either minimize the cost or maximize the probability. So I'm talking about maximizing the probability because the cost is maximize the log probability because the cost is the negative of the log probability. So I'm just sort of switching metaphors a little bit over here, but it's the same problem. We haven't changed anything. It's still a very simple problem that we began with. Now I'm going to make it more complex. Instead of trying to separately, compute the best path cost for odd and the best path cost for even, in which case I'd be composing two graphs, I can try to merge the two into one graph, like so, right? If I merge the two into one graph and I find just the best path through this graph, the best path through this graph not only tells me the cost of the best word, it also tells me which word was spoken. Does that make sense? Right. You guys want a break? Go wash your face. I'm overloading you. 10 minutes. If you want a break, let me know. Yes, no. I'm going to assume it's a no. Okay. All right. So is this clear? The leap from here to here, was that too big for any of you? Tanmay, was it big for you? Kathleen? Yes. Thank you. Right? So did this make sense? It did, correct?
Yes, that made sense.
So I'm just starting off from some point. This was the graph which showed how you could align the model for odd with the input. This was the graph which showed how you could align the model for even with the input. Correct? So I also want to factor in which word is more frequent. So I have this extra edge where I put in the log probability of the word just to factor in the natural frequency of these words. It's just a penalty that I'm applying on this edge. So far, you're still with me, correct? And then I can find the best path through this guy. And that best path is going to have a score. I find the best path through this guy, and that best path is going to have a score. And I pick the word for which the score is, the cost is lowest or the score is highest, depending on how you look at it. That is clear, Leon? Right, Le?
Yes.
Okay, Kathleen. Oh, you're allowed to say no. I can go back. I have time. Right? Okay. What time is it there?
It's 9:15 p.m.
Oh my good God. You don't have time. Okay. All right. So now here's what I did. I can just, this dot over here and this dot over here don't really represent anything. They just represent a beginning. Correct? So also this dot and this dot simply represent the ending of the graph.
Okay.
So if I say this dot is the same as this dot, and this dot is the same as this dot, you're going to end up with this graph. I just stack the two graphs one on top of the other.
Okay.
Kathleen, makes sense? Correct? But then it just became one larger graph, correct? And I can find a path through this larger graph. And if the best path goes through the green region of the graph, you know that the word was odd. If the best path goes through the blue region of the graph, it was the word even. Make sense? Right?
Yeah, it does.
And so now instead of doing two graph searches, you've done one.
So does the fact that odd went on top imply that that is the less frequent one?
No, it doesn't. That one is actually, that cost is sort of built into this edge, this green edge. I could have drawn it either way.
But does the fact that the edge is longer imply higher cost or no?
It doesn't over here. I just had to draw it somehow, right?
Okay.
I mean, you can imagine side them side by side. It doesn't, it's the same thing. Yeah, okay. So this is easy so far. This is the same as saying that I now have this template. Look at this figure on top. It's like saying that instead of just aligning this guy, this model on the left with my input, I'm aligning this model on top with my input. It's like composing a graph for this model. Every time I have an edge like this, I'm going to put an edge out here, right? Okay, but anyway, let's stay with that. So I can just compute the score of the best path, pick the best, compare and pick the best one, okay? So far, you're with me. Now, suppose I want to recognize not words, but word sequences. Then what happens? Instead of recognizing individual digits, you want to actually recognize a telephone number. That's not an individual digit. So how could you do that? That's a big leap, right? From one word to many words. It turns out it's not such a big leap. And so you basically want to do the same thing. Instead of being a single word, your class is a word sequence. That's all that happened. Right? Nothing changed. And so suppose, but then here's the problem. Suppose I want to recognize telephone digits and you have 1,000 phone numbers. Suppose I want to recognize telephone phone numbers and you have 1,000 phone numbers on your phone, people that you could call. Are you going to be recording all 1,000 independently as templates? That doesn't make sense. You know that all 1,000 are composed of the same 10 words, 10 digits, correct? So what you can do is to simply record the individual digits. For each digit, you're going to get a template. You can attach them in different ways to compose the different phone numbers, right? So that means you only built 10 models, but now you can construct 1 million phone numbers. Make sense? Right. And so, see, that's exactly what we will do. So now I'm going to use this completely corny example where you want to have recognize either rock star or dog star. Okay, it's a corny example. I don't know why I came up with it, but I have it, and well, it conveys the concept. So what would you do? You record examples of rock, you build a model for rock. You record examples for dog, you build a model for dog. And then you build a model for star. Then you can just attach the model for rock and star, and you get a model for rock star. You can attach the model for dog and star, you get a model for dog star, right? And then when I get an input, I can align it against the model for rock star. I can align it against the model for dog star, and whichever gives me the higher math score or the lower cost, I am going to use that. I'm going to recognize it as that corresponding word sequence. You still want to factor in the priors, right? So people say rock star more frequently than dog star. I think in our world, they say rock star much more frequently than dog star. So you want to have the probability of rock star out on this edge, the probability of dog star out on this edge. You're with me, right? And, or I can use Bayes' rule. I can have the probability of rock out here and the probability of star given rock out here. Because the probability of rock times the probability of star given rock is the probability of rock star, right? I can spread this thing out in the same way. It doesn't really matter. And just like we just saw, I can stack the two graphs in this manner, and the search is going to stay the same. Nothing has changed, right? But then let's observe something very interesting. What am I doing? When I find the best path through this graph, I'm finding the best path through the upper graph, I'm finding the best path through the lower graph, and I'm picking the better of the two to decide if the person said rock star or dog star, right? That's all I'm doing. And when you realize this, something very interesting happens. So consider this. When I'm aligning this input to say dog star, I could have aligned it in many different ways. I could have aligned the first three vectors to dog and the next several vectors to star, which is to say the transition happened here, right, between dog and star. Or I can say I align the first four vectors to dog and the subsequent vectors to star. Or I can align the first five vectors to dog and the subsequent vectors to star. There are different ways of aligning my input to the word sequence dog star, correct? Each of these alignments has a different score, and when I pick the best alignment, I'm picking the best of the lot. So basically, if I just said, I want the first three vectors to be aligned to dog, and the next four vectors to be aligned to star, then I'm forcing the transition to be here, and this might be my best alignment. If I say I want the first four vectors to go to dog and subsequent ones to go to star, this might be my best alignment. If I want my first five to go to dog and the subsequent ones to go to star, this might be my best alignment. If I want my first six to go to dog and the subsequent ones to go to star, this might be my best alignment. And so when I'm finding the best overall alignment of the input to dog star, I'm picking one of these four best alignments, which could be this guy. So you see what's happening over here. The best alignment of the input to dog star is either the best alignment that went from dog to star at this time, or the best alignment that went from dog to star at this time, or the best alignment that went from dog to star at this time, or the best alignment that went from dog to star at this time. It has to be one of these four. And so you're picking the max of these four, right? That makes sense to you guys, Leon? Right, you guys over in Africa falling asleep. No. Make sense?
Yes.
Was that not meant to say I'm not falling asleep, or was it meant to say I didn't get it?
No, I'm not falling asleep. I got it.
Okay, fine. Right. Okay, so the same thing over here. I have 4 possible times at which I could go from rock to star. And so each of those has its own 4 possible best alignments, and I'm picking the best of those guys. And so the overall, when I compare the best alignment through rock star with the best alignment through dog star, I'm comparing the max of these guys versus the max of these guys, correct? But it turns out that the whole thing is kind of commutative. So what do I mean by that? Instead of, I could say this. I can say that I know that the word star began at the 4th time. If I tell you that the word star began at time 4, then I can decide between dog and rock right here, right? Because I know that the next 4 vectors belong to the word star. Make sense? If I tell you that vectors 4 onwards belong to the word star, then after vector 3, I can already decide if it was rock or dog, because the next 4 belong to star, which means that you look at this trellis. Now look at this very carefully. That means that once I decide that the transition happened over here, this portion of the graph, I can make the comparison right here at this point, which means I don't need to compute the second half of this graph over here at all. I can delete it. I can make the comparison right here and just use this portion of the graph.
So just a comment from me, more or less, yeah, just a comment. So what you're saying is that you look at the portion of the 2 graphs that are similar, then you can take it off and you can make the decision where the portion of the audio graph changes to the other rock star, which is here.
Yes, pretty much, right? So here is what happens, right? I can say that if I know that this portion, if I know that the transition happens here, then the rest of this graph is going to be identical in both cases. And so I can ignore the colored portion. I can just use the black portions of the graph and this portion of the graph over here, right? I don't even need to consider this one.
Exactly, yeah, exactly.
Same thing. Suppose I tell you that the transition happened at time 2, right? At this way, at time 1, 2, 3, 4, 5. Suppose I told you that the transition from dog to star happened at time 4. Then I can make the comparison right here and eliminate this portion of the graph, correct? If I told you the transition happened at time 5, I can make the comparison right here and eliminate this portion of the graph. If I told you the transition happened at time 6, this is going to be my comparison. So what happened in the process? The second copy of star completely disappeared. See what happened here? And so something magical happened. Although I'm still recognizing rock star versus dog star, the graph became smaller because an entire portion of this graph disappeared. The star that was shared. And so here is my reduced graph, and this is what I'm actually going to be using for recognition. Now, this was only possible because I used exactly the same model for star in both cases, right? Because only then can I be sure that these 2 graphs are going to be identical. I recorded star once, and I used that model twice to make to compose rock star versus dog star. And when I do that, I don't actually need to explicitly use the word star twice. I can just use this reduced graph. And the best path through this reduced graph is going to tell you whether it was rock star or dog star. Make sense? Right? And this is the magic. This is all we really need to know. Look at the figure to the left. I said there are two ways of aligning this input. You can go through rock and then go to star, or you can go to dog and then go to star. This graph is the same as this guy, or I can represent it like so. This graph is the same as this one, right? You see what I'm talking about? And so if I compose this graph, and if I want to align the input to this graph, what I'm really doing is I'm going to be stretching this graph out in this vertical manner, composing this more complex graph, which compares this guy to the input, and finding the best path through it. And the best path will tell me which was what was spoken. Okay. And once you realize you can do that, things become easy. So here's what I do. If I want to recognize rock star versus dog star, I record many instances of rock, build a model for rock. I record many instances of dog, build a model for dog. I record many instances of star, build a model for star. Then I connect up the templates in this manner, the models in this manner. On these edges, I put probabilities because I want to factor in the priors, right? So this is going to be the probability of dog, this is rock, this is star given dog, this is star given rock. And I'm going to use this guy in this structure, and I'm going to find the best path through it, and it will tell me what was spoken. Okay. And once I know how to do that, I can build something much more complex, something that recognizes poetry, right? This is from, the Charge of the Light Brigade, Tennyson. So I can just build models for all of these words, connect them up in this manner. And now I can use this to recognize what was spoken. Okay. I am going to sort of skip the rest of this because I can see from your poor faces that at this point, if I continue, you're going to fall over. What I will do is just convey the idea that, if you look through these figures, you can see what is happening. I can compose graphs for all sorts of things and recognize any sequence of words, correct? And how do I extend that to natural language? For natural language, something interesting happens. Suppose I want to recognize natural language, then I have to build a graph where I have every possible sentence in the world in my graph. That's clearly not going to be happening because that's infinitely big, correct? So we're going to do something cheap. First, I'm going to represent my language as a tree. So imagine you have a language where you have only two words, sing and song. Then the complete set of all possible sentences can be represented as a tree, right? The first word could be sing or song. Then the second word could be either sing or song, and it could be, and so you could have either song sing or song song, or you could have sing sing or sing song, right? And so this whole thing is a tree, right? This is my graph. This graph represents, so if I want to recognize natural language, I'd be building models for all of my words and building this graph, but this graph doesn't help. It's still infinitely big. So I'm going to simplify things. I'm going to build something called an n-gram language model, right? So if I want to find remember, we want to assign penalties for every word sequence, correct? And so for this path, I want to have the penalty of the probability of sing, sing, sing. Every path has its own unique penalty. It turns out you can smear those things out. And again, without going into too much detail, it turns out that if you make something called the n-gram assumption, the graphs become really, really small. Something like these. Now, if you were in a classroom, I'd have made these things much more explicit by drawing things on the board. Since you aren't, and since you're sleepy, you're going to have to believe me. But by making unigram, bigram, and trigram assumptions, these graphs become really small. And then the problem of recognizing speech simply becomes that of finding the best path through this graph. So again, the way you will do it, you're going to build record instances of every word. You're going to build a model for every word. You're going to then use those models to compose this graph. Then you're going to use the alignment algorithm that we saw a long time ago. And you're going to find the best path through the graph when you align the input to the graph. And that best path will tell you what words were spoken. Okay. This is at a very high level. This is what happens in speech recognition. I'm going to hand over to Hira, for whom it's afternoon, so she's not going to be falling asleep.
Yeah.
But, and she's going to show you how to build. I'll stop sharing. She's going to show you how to build the recognizer using Kaldi. And the general concept that you just saw, that's what is going to be followed. The details can get very complex. Don't worry about the details right now. Follow the procedure at the end of the exercise. You should be able to build yourself a little recognizer using the toolkit that, on a small data set. And then later, when we're properly set up, you should be able to repeat this on a much larger data set. And you will, hopefully, in a couple of days, be able to build yourself a speech recognizer for pretty much any language. Okay? Thank you. Here, the floor is yours.
Okay. Hi, guys. So how many of you used the Kaldi toolkit before? If you have.
I'm sorry?
Have any of you used the Kaldi toolkit before? No.
I have not.
No. Okay, so I have set it up. I was set up now on the Clio machine, and the data is also there. So what we can do right now is log in there. So if all of you can log into the Clio machine. And just unmute yourself so we can talk through this. You can tell me what errors you're getting, and once you do log in, let me know.
I'm logged in.
I'm logged in.
So the Kaldi toolkit is under my directory right now, and it has execute permissions for all of you.
Folks, just in a brief interruption, I'm going to take a 15-minute break to grab some food, but I'll be right back.
Okay. And so if you do ls/home/hyd, you'll be able to see a couple of files. And one of them is library_speech_tutorial.md. Do you see that?
Yeah. Is it maybe?
Hello. Sorry, can you paste it in the chat?
Yeah. Would it basically be easier if you shared your screen? So
Yeah.
that,
Yeah. I'll do that. Okay, can you guys see my screen?
No, it's black.
It just says
Not
your
yet.
screen sharing, but it doesn't show anything.
Interesting.
Now we're good.
Yeah, okay, great.
Hey, can you zoom in a bit? It's quite small. Can you zoom in a bit?
How do I zoom in? Let's see.
Sounds like Command plus, Command Shift
Control plus. Yeah, depends on what.
or Control plus. Depending. Oh, you're on Windows.
Yeah, and I'm not sure if.
If you could right click again, I think I saw change settings under saved sessions. Yeah.
Okay, while this is getting done, let's see if you guys can see the tutorial, the MD file at ls/home/hyd.
What's the file called?
It's called library_speech_tutorial.md.
So I don't have access to Clio.
Okay.
Is it needed for this?
No, it's not needed. What I can do is give you the email you the tutorial, and you can follow through it. But on Clear,
Sure.
I set up the Kaldi before, so all of these guys won't have to go through every little step. So let's see.
That's all right. We can do it later also.
Okay. So what we have here is we have the data set, which is called Library Speech, and it has two sets. It has train clean 5, and it has so let's just see how many files, how many audio files it has. It has almost 141 training data, and the dev has almost 48 files. So what we are going to do is train speech recognizer from the training data and try to get the alignments and the text out of both. And what we have here is the Kaldi toolkit. You guys all have access to it. What it does it right now, what we are going to do is we're going to use the recipes that are already built in. And these recipes, what they mean is they already define the entire process flow for building a speech recognizer, and they already have defined the data set that you're going to use for this recognizer. So it becomes very easy to follow through. And where you will find these recipes is under eggs.
Hira, could you send on the chat the actual, like, do a PWD and like send the actual complete
path?
Okay. Yeah.
Okay. So let's see if I can do this.
Or I can do that. Okay, that's fine. I found it.
All right. Yeah. Perfect. Right. So inside Kaldi, we'll have EGS. We'll have a lot of these recipes. You can find multiple recipes here. And the one we are going to follow today is called Mini Library Speech 2. Mini Library Speech 2 is just a copy that I've made out of Mini Library Speech, which was already present. The way you can follow through this tutorial is also make a copy of this directory and call it Mini Library Speech _ your name. So you will be under this directory, but on a following the recipe, but on a separate path. Okay. So we have a couple of files here. What you will see here is that these are already present, and all of the experimental results will actually come under here once you are done. So if you look up at the MD file, can you guys see my screen here? Yeah, okay. So I have a couple. So Tanmay, if you are starting from scratch, you can git clone, you can install all of the libraries, and then, okay. So from here, from running experimental library speech, this is what everyone has to do. But before that, Tanmay, you can do that. After, what you have to do is export these Kaldi paths, and let me copy this there. So my Kaldi root is /home/HYD. And then after that, I can just simply copy these two paths. Okay. And then you will see that there's these two cmd.sh and path.sh. So we'll just see what is in there. This is just, so if you are running on Clio right now, just keep it like this. It uses CPUs to do all of the things, and that's what we want.
Isn't your Kaldi root like home/HYD/Kaldi?
Yes, you're right. Sorry. So it is this. So let me just do this again. Okay. And you just need to run this cmd.sh and path.sh, which is already defined, but it just defines your path again. So Kaldi root is already defined here, but it's like not the direct path. So we will also.
Do we also need to export?
Yes.
Or is it okay for Kaldi?
No, you'll have to do that. You'll have to do the export. Okay. Let me know if any of you have trouble with this. So just to see if we are getting the correct things, we'll just do echo, and we'll see that echo train CMD is run.pl, and we're defining some memory here, which we'll use for the commands that are coming. Okay, so since I've already downloaded the data, you don't need to go through this. We also download a language model, already pre-trained language model, and you can follow, it downloads it from this URL. You can follow these two commands to download the language model and the data. But for now, we won't do that. And also, just a comment, if you download from this, what it will do is download into a directory called library speech. Now, I already have that, but this download will have 1,000 training files and almost, I think, 400 testing files. But for this experiment, I've created a smaller version of it, which is 140 dev files. So for now, I would recommend that you just use that, which you will be able to find under my directory. Okay, so this is the first step where we will format our training and our dev data. What does formatting mean? Let's just run this command and we'll see the output of this. What I can actually do is, let's see. I can exactly copy this over there. Okay, after running this command, what you'll see is you'll get something under data file under dev clean 2, and you'll have a couple of these files. So if you look at wave.scp, these are path to the wave files in the data. And if you count how many there are, it should be 48, yes. And if you do this in the train, you'll see almost similar number, which is 141. And it defines a couple of other things, and this is very important because this step, if you are training an ASR for your own low resource language, these are the files you would need to define. You will need to define wave.scp, which is path to your wave files, utterance to speaker. Let's see what that is. That is, the first column is the utterance and the second column is the speaker ID. Kaldi uses it for training its speaker specific models. You'll also have a speaker to utterance, which is exactly the opposite mapping. So we only have 2 speakers here. So you have 2 speakers and then all of their files. This is speaker 1, this is speaker 2. And you also have the text, which is the audio file and the text that is being said in the audio file. There are inbuilt scripts that will give you these files, but for now, I'm just telling you that these are very important to prep the data to be used later on. Does it make sense? Are you guys following? Yeah?
You're moving really fast.
Right. Are you guys writing the commands too, just on your screen to follow through, or just looking at my screen?
Just looking at your screen. You did go a little fast, so.
Okay.
Well, I think so. The good thing is we are recording this, so you can do this after at your own pace, or follow the tutorial that actually has all the commands.
Exactly.
Okay,
I'm just
so
copy pasting from there, and it should be, I've done it twice, so it should be pretty clean off. It should be pretty clear. But even if after that you have questions, just you can shoot me an email.
I'm actually taking screenshots and following through in my head.
Okay, that's great. So what I'll do now is, so this was just how to prepare the data. Then there is another thing of how do you prepare your dictionary, which is how do you prepare your phonemes and how do you define the silence phonemes, the non-silence phonemes. This is all just segmentation that needs to be done to train, to be used later on in the recognizer. So what I will do now is, you can read through this. I think this is pretty clear. It tells you what you should look for after running each command. What I'll do now is, instead of running these commands, I will just show you the output of this. I think that will be much easier. So you'll know what to look for after running the command, right? Yeah, does that make sense?
Yeah.
Okay. Let's see. And you can also see the time some of these commands take. So each of these commands should take 30 to 40 seconds, or sometimes it takes 1 to 2 minutes. So you can look at that. After preparing the language model, I'm actually going to go to my own machine where I've already run this. Let me do the settings again here. Okay. So we have formatted the data, right? We are into the second, which is preparing the dictionary to use in this experiment. So you will run this command, that is local prepare dictionary. After seeing the success message, you should look into data/local/dictionary. So let's just look here. What does this contain after we've run the command? So it has a couple of things, right? It has a lexicon.txt, which should be, it's all of the words and the phonemes that are used for saying the words, right? So if you look at, let's say Abba here, it's like there are 3 phonemes that are used in saying this word. And so it's like a mapping of word and phoneme sequences. If you look at non-silence phonemes, it's a bunch of, so this is the phonemes that are used in the data that we have in the training data, which is about 140 files. So if you see here, some of these have more than 1 phoneme per line. It's just the same phoneme, but a different stress is being used. So we have a, but then there is a 0, 1, 2, which means there's a different stress for the same phoneme. And then we have a b, which doesn't have any stress no stress example in the training data. And so you have non-silence phonemes here. If you look at silence phonemes, there are only 2 silence phonemes that whenever the person is saying something and is silent, one of these phonemes will be used. And then in the beginning of when you're not saying anything, the silence phoneme will be inserted. So these are the couple of files that you'll see. Let's see what this is, extra questions. These are exactly the same as the non-silence phonemes, but just defined differently. So you can actually find a greater description of all of these under this link here, that you can find in the MD file. And there should also be a phone.txt. Okay. Does this make sense?
Mm-hmm.
Yeah. So after you run this command, after you run this local prepare dictionary command and then prepare language command, you should be able to see, you should just check data local dictionary and data lang directories and see if you have all of the files. And to understand the meaning of all of the files, you can actually look at this link. Yeah. Okay. So I told you about this data local dictionary directory, but let's just look at data lang directory. So it has all of the phonemes that you would be using in the ASR. So there are about 364 phonemes, and you'll see that all of them have like silence has a beginning, B means beginning, E means end, I means in between, intermediate, and S means it is a singleton, it's a separate word. And you'll find all of these BEIS with after each of the phonemes. And so this is a list of all of the phonemes that you'll have in your ASR recognition. There are also like words.txt, which are all of the words. Yeah. And this word.txt and the non-silence phones that we see should have like equal correspondence, same amount of files, amount of lines. And now let's look at this topo file. So this is the HMM that it defines the HMM for all of the phonemes. So if you see, there are two topology entries here. One is from 11 to 346. 11 until 346 are the phoneme IDs, We saw that there were almost 346 phonemes there, right? And this defines the transition and emission probabilities for each of the phonemes. And down, we see another topology entry from 1 to 10. You don't have to write this. This is all created by itself. And it's just, this is just how to understand it. So there are let's just look at one for phonemes table. From 11 to 346, you have 4 states, right? One is the first one, 0 is the entry state. And this is the 0, 1, 2, 0, 1, 2 is the same. But you have a transition from 0 to 0, which means a self transition, and it has a probability of 0.75. And then you have an emission, like going to the next state, and that has a probability of 0.25. And then for the next phoneme, for the next state, you also have self transition, which is 0.75, and then going to the next transition, which is 0.25. And it's exactly the same way for all of the phonemes. These 1 to 10 are like the silent phonemes, and they have some special matrix here. But that's the way to understand it. And a good example is actually here. I think you guys can, yeah. So the topo graph that you just saw, this is a better and a cleaner version of it. And to read through this, to understand what's happening, you can read through this link, and it's also in the tutorial file. Does it make sense? Yeah. Okay, so this is prepare the dictionary to use in this experiment part. We have done the 2 commands here. After that, you want to format the language model in, the script converts the ARPA format language models into an OpenFST format. And it's just a format that Kaldi uses. This is nothing technical, but you need to run this. And this command takes some time, but make sure that you get a success message at the end. Now the first part comes when we are at the feature extraction part, and we want to extract features from our WAV files, right? So once you do this, what you'll see is you'll see the MFCC, which is a feature that we are extracting from the WAV files, and you will see them under this directory, MFCC. Yeah. And these are all of the features that are extracted from the train and from the dev. There is a way to read them and because these are not text files, you open them, these are binary files, you won't be able to, but there is a command here that tells you how to read them. So if I could show you this, maybe this will work. Let's see. But to see that everything is working out fine and you're getting what you should be getting, you can use this command. Oh, okay. So let's see. It should be right. I think I don't have the paths right. That's why it's not working properly. Let me actually export the path correctly. And the first 2 paths that we have. Now will the command work? Okay, so this one didn't have anything. Let's see if I can get something out of this one. No, this one also doesn't have anything. Do I need to use ARC files? Okay, so I'm kind of using the other file.
I think you're just running it from the wrong directory.
No, I think I'm in the right one. It's just that they're empty. I found something that does, let me actually.
Oh.
Okay, so this one has something. So what it does, it prints out the if actually the form my font was a bit smaller, you'll be able to see. So MFCCs are like 13-dimensional. You'll get 30 numbers per time frame, and just use this command to see if your feature extraction is fine. Does that make sense? Yeah. Okay. So this feature extraction would take about 30 seconds on the dev clean 2. Since you only have like 48 files, it'll be very quick. But once you start doing this on larger data, it'll take some time. And after this, you'll just do compute CMVN stats, which is also pretty quick, and it is also saved in the same MFCC directory. So once you are done, you should have a directory here called MFCC and all of the features inside it. Okay. After this, what you want to do is you want to train your monophone acoustic model. That is the first part in the ASR. How do we train the acoustic model? You want to run this. First, you want to get the shortest 50 utterances because they're most likely to have accurate alignments. This is just a step that you do in Kaldi to make sure that you get clean alignments from the data that you have. After you've done that, inside data, so if you look here at the command, it is creating data clean, and it is taking data / train clean 5 and creating data / train 50 short. So after this command runs, you would see something here, which is exactly the same as what we got after formatting the data. But now it will have less number of files, and these files will be used in the monophone training. So now if we train the acoustic model using this step, what we will get here is, okay, this is going to take some time, but I already have the results, so I don't have to wait for it. But this is going to train the model, align it, train the model, align it, and save it in some file. So, but is this making sense? Yeah, okay. So what we can do is wait for it. So after we are done with this step, we will actually align our training data using the model that we have trained. Okay, so this is done. This is done training, and let's see if this one works. But this is also going to take some time. But after this is done, we'll be able to see some alignment results here, which is very cool. Okay, this is done. So let's see. Oh, so my font is so big that it's not very good looking here. But what you can see here is that the first, can you guys see the file? Yeah, okay. So the first is the first column is the file name. And the second, these are all phoneme IDs. And what we have here is, so if you see here, we have an opening bracket here that goes all the way until here, and it closes here. And if we look down, we have a silence all the way here. And then the next one, opening bracket, starts here, which means that we have this phoneme starting from here. And then it goes all the way here, and then we have another phoneme starting here. So this file is kind of like a visualization of how your alignment looks like for this audio file. Does this make sense? You don't have to directly use it, it's just a way of visualizing your results. And it does this for all of the audio files. Does this make sense? Okay. So once we've done the alignment with the monophone model, we also want to train the triphone acoustic model. And these are a bunch of commands that you would use. Since we're not running it, I guess it's fine because the output of these, it's exactly the same as the monophone acoustic model. And these will also take the same amount of time. So you will do this couple of times with different feature sets. Once you'll do it with delta based triphones, and then you'll do it LDAM, LLT triphones. And at the end, you will get a model that is called Tree 3B. Or should I go through each of the commands just to be sure that we are getting it? Or because the output of these look exactly the same as the monophone acoustic model. Does this make sense? Okay. You can go through, you have to go through each of the files. You cannot, each of the commands here, you cannot skip any, otherwise you'll get an error. Yeah, okay. One thing, so after all of these training have been done and alignment has been done, what you'll do is run this generate graph command, which is mkgraph, and this graph contains, it will build a, the kind of graph that Professor Bhiksha was showing, where you do the alignment for all of the phonemes. So it will make a graph like that for all of the states. And after you have the graph, you can decode the way that Professor Bhiksha was explaining. How do you decode from and get the best path from this graph? Once you have the graph, you need to get the best path out of it, given your utterance. And that you can do through this step. So what I will do here is, since this is just there are two ways of doing this. One is the HMM and the other one is the neural model. So you can follow all of these commands to do the HMM one, but I will follow through the neural model one. And that is also listed here. So what I will do is, I will run all of the commands for the neural model and see how the model trains, and we'll see the decoding step as well. So let's see if we can run this. Okay. What this is doing is, it's creating another set of features that is used in the neural model training. You can choose to skip it, but I'm just doing this right now. And you will also find all of these commands here in the tutorial setup. So first you do parameter setup, that I just did with the command, and the features that it's extracting right now is called I-vector extraction, I-vector features. And those will take some time, but we'll wait through it. Once that is done, we will create the the same HMM topology that we saw in the other monophone model that I was showing you, that each of the states have an emit and a transition probability to the next state. You'll exactly get the same kind of model here for all of the phonemes. We'll wait through this command and then go to the next one. Okay. So train the graph, it's doing the final alignment. And also another thing about Kaldi is that it does not print its errors well. And whenever you get an error, you have to look at the log files. So wherever you're running a command from, see there will be a log directory, and inside it there will be .log files, which you can go through and see what the error is. Okay, after this, we'll just train the neural model and we'll see the decode outputs. So that should be quick. Okay, so let's see if we can train our neural model. All of the stats, all of the parameters for training the neural model are in this tutorial file. But what you can do is actually change it. Right now, I'm only training it for 3 epochs, just so it is quick. You can also change that, train it for more, change the learning rate. So in the train, I've defined all of these, but you can change them here. So let's see. Since I have the results, I don't think I have to wait for it to be done. After you run this, so right now it's running this command. What you'll do is you'll make the graph again, just as you did in the acoustic model and the monophone model. And then after this, you will decode it. Okay, so see here, it's running through the first iteration now. And it will go through 5 of these iterations. Once you have all of this, you can look at the results of decoding, which I think I'll show you now. Okay, I have some warnings and I have some errors. If it doesn't stop, that's fine. There is a warning about a file, I think. But since this is training, I'll show you the okay. I'll show you the outputs. So after you train and decode, you'll see outputs like this. So it's for each of the file, it's telling you what the best path is, and it's putting this putting the text here. And you'll see it in number of decode files, but these are the output files that you should be looking for. And for each of the training, it also puts out what is the best word error rate, which we can see here. So the word error rate was almost like 70%. And if you have more training data, it'll be higher. And this is the kind of word error rates. This is just an example. So if you're training on the data that I've provided, you should be looking at results like this. And also these results, and also like the text outputs that you see here. And you can also look at the output of the test transcripts. So this is the training one, but if you want to look at what does the test one look like, so this is the dev outputs, and these should be the output of the, okay, so these are 48 lines. So for each of the audio file in the dev, which were 48 audio files, you have the alignment here, the best output, the best path here. And the word error rate is also calculated from these files and the true transcript. Okay, so just to go back and see if our training is done. Yeah, so training is done for each of the audio file. And after this, you'll run, right, so this was this step, and after this you'll run this, and you'll decode, which is exactly this, and then you'll look at the output files, and you should be seeing the results that I have here. Does that make sense? Yeah. Okay, so since you did not follow through, the best way to do is, since on Clio all of the installations are there, just go into this path. Let me put this in the chat. And whatever I've shown you is there. You'll be able to look at it there, the results. What I would recommend is create another directory under the same path, but just call it mini_library_speech _ your name. And from there you can start following the commands. The data is present here. So the data should be, oh, I'm not in the Clio machine. Yeah, so the data is here. Yeah. So these are the starting steps, and then follow through the tutorial, which you can also find under /home/HYD. So let me actually just write that. Okay, this MD file should be explanatory. Yeah, does that make sense?
It does very much. Thank you very much, Kira. I remember when I was first trying to build my first speech recognition systems, like 4 years ago, trying to figure out Kaldi on my own. And now I wish I had this, like, okay, I know we went through it very, very fast.
Right.
But just having this tutorial so you can go follow it, like, you know, everybody can try to do this over the weekend a little bit, or, you know, tomorrow, you know, or during next week at some point, if you want to work on speech recognition. I think it will be very easy, because really all you'll need to do if you want to do this on another data set, you know, it will be just change the pointers to the data and eventually modify the parameters in order to do slightly better.
Yeah. Yeah, and it takes some time to get hold of what the errors mean. But once you try to understand them, I think you get same kind of errors over and over again. So once you start fixing it, it'll be fine. And also just look at the, I have listed most of the things that you need help with understanding in ASR, especially the way that they have defined all of the classes. What does topo means? What is HMM topology? How do they define it? What phonemes are they using? What does non-silence phoneme and silence phonemes mean? All of those explanations are in the links that I've linked, so you can go through them. Yeah. And shoot me an email if you have a question, especially on this Libre speech data. Yeah.
Cool. Kathleen, Leon, Yadela, Tanmay, is there anything? I mean, I understand it was like super fast, but is there anything else? Is there anything you'd like to ask? All right. Well, I hope that you'll try this. You know, it really isn't a lot if you just copy commands, and eventually it will be really good. As Bhiksha said, and you know, it's hard to be able to do all of the things in just 2 hours. So, yeah. Did you want to add anything, Bhiksha?
No, I mean, Tira did a very good job.
All right. Well, thank you very much.
Thank you, everybody.
Thank you.
Thank
And,
you.
Thank you.
Yeah. So, thank you again, Bhiksha and Hira, for this. This was great.